Okay, so last time we talked about this double well problem because we already solved the single well potential problem, right? And in both positive and negative energy as an incoming particle states, and we know very well that the ground state of a single potential well with a finite potential is given by this cosine function inside this well and then exponential decay out of the well. Suppose that I connect these two single well potential and to form a faraway double well. So, and we could take advantage of what we have learned in the single well problem, and then we could guess or we could construct approximately the solution, the ground state and the first excited state of a faraway double well problem. And we'll see later that the states that in either one of these two wells is not stable, and this particle inside one of the well could actually go back and forth, oscillate between these two wells. And this phenomena is called the oscillations, quantum oscillation. And this kind of oscillations actually observed in many, many quantum mechanical materials such as molecules and so on. If we have two stable states that the molecule can actually sit, then these particles can actually oscillate between these two stable quantum wells, or called quantum two-level system. So this is the simplest example of a quantum two-well system, that the particle is trapped in one of the well is not trapped forever. It can actually go through this oscillation between these two wells. And the reason why this particle can actually go back and forth between these two wells is because the overlap between these two approximated single well wave functions. So if I label this wave function, the ground state wave function of the left well UL, and you write as the right ground state wave function of this single well potential, then I can construct even odd combination of these two states, right? So by forming this even odd combination of this U right and U left, we can make a ground state and the first excited state of the double well problem. Okay, so this is the ground state. U even is the ground state of the double well, and U odd is the first excited state of this two well. So let me just sketch the ground state and the first excited state wave function of the double well based on this construction of a single well ground state wave functions. So this is the ground state, and if you take odd combination, you'll find that this should be the first excited state. Okay, so this is a sketch of this U even and the U odd in a double well problem based on the solution of the single well U left and U right. And remember, this kind of even odd parity eigenfunctions have been discussed earlier. In particular, I mentioned that this kind of even function, U even, is actually a very stable state compared to the single well, because you have this very flat region in between these two wells, and you have a very steep exponential fall off outside of this double well, so that this binding energy of this double well is actually very large. And you also know that in a single well potential problem, the ground state must be even, right? And the first excited state must be odd. And the reason is because, as I mentioned earlier, that for this even parity eigenfunction, if you calculate this slope or first derivative of this wave function with respect to x, and you'll find that kinetic energy is actually lower, because U even shows a smaller derivative or square of the first derivative. Remember, the slope of the first derivative of the wave function has the meaning of the velocity or momentum, right? So when the slope is actually take a smaller value, you have a lower kinetic energy. But if you look at this odd wave function right there, and it has more nodes, right? Has more sort of is curved more. So if you evaluate this du r dx, and if you integrate over the entire range of potential, you will find that this value du r dx squared is larger, meaning that it carries more kinetic energy. As a result, this cosine function must be the ground state, and the sine-like function must be the first excited state, as we already pointed out. So in a very similar situation to the single well problem, this double well also shows such even parity symmetry as a ground state and odd parity symmetry states as first excited state. And this is the simplest way that we can construct approximately the ground state and the first excited state of the double well problem without actually solving this problem. Okay? So you can see that I haven't solved anything of this double well problem, but if I do, I can still get the similar solution like this, but not exactly this u even u odd, because u even u odd are simply just approximation. So this is not exact, but it's very close to the exact solutions of the double well if you really rigorously solve this Schrödinger equations of the double well, and you will find approximately the same type of ground state first excited state wave functions. But of course, we can take advantage of the solution of a single well problem and then constructed eigenstates of this double well, provided that this approximation is good. And the condition that this approximation is good is that the overlap between these two u left and u right is really small. So the small overlap between these two ground state wave functions on the left and right indicates that these two wave functions are more or less independent, but not quite. So they are not exactly independent, but more or less we could treat them approximately independent. But they are not independent because they have a finite overlap between these two ground state wave functions on the left and right. As a result, you can consider the situation where initially you have a particle, say, sitting on the left well, and which is described by this u left in the beginning. However, because there is a finite, even though this is a small overlap, but this is a finite overlap, and this particle can actually go to the other side because there is an overlap wave function, so that the product between these two wave functions is non-zero. So you have a finite probability to find this particle in the middle. Okay? As a result, the particle probability actually keep spreading out to the other side. So as a result, you can actually find this particle at some time later. And we'll see and derive this oscillation in just a moment, that this particle is not just sitting still on this right well, but it will oscillate between these two wells. Okay, so there is a oscillation frequency associated with this kind of a quantum oscillation phenomena, and we could get that frequency based on this construction. And so this capital N even and odd is the normalization factor, the wave function normalization factor, which is almost square root of 2 in the denominator when these two wells are really far away with each other. So this is the reason why we need to consider the far away to well if these two wells are too close to each other. So these two wave functions overlap too much, and this approximation is not good enough. Okay, so this approximation is good only if these two isolated wave function overlap, the almost isolated wave function get a small, very small overlap. So let's derive this quantum oscillation phenomena for small but finite overlap. And you know that this E even is not the same as E odd, where capital E refers to the eigenenergy of the even parity states. U even and E odd corresponds to the energy of the U odd state. So let's just try to derive such a oscillation phenomena. As I mentioned, U right is the initial state of this two-well problem. It's not stationary state, but it will actually travel to the other side and then goes back and so on and so forth. So let's just derive such phenomena. At t equals 0, suppose the particle is on the right well. So as a result, this U of x is actually U right, which is U even plus U odd divided by 1 over square root 2, which is the initial state. Okay, suppose that initially the particle is on the right well, then let's just time evolve the states to t equals to t, where t is larger than 0. So you can follow time evolution of a Schrödinger states. You can multiply this initial state by the time evolution operator. As I mentioned, this energy of this U even, capital EE, is not the same as capital E odd, because capital EE is the ground state. Should be less than capital E odd for this argument that I just presented. Because of parity consideration, this even parity states must be the ground state, and the odd parity state must be the first excited state. Okay? As a result, this capital E even is actually smaller than the capital E odd. So you need to actually time evolve this, not just U right or U left, because U right and U left are no longer the eigenstates. Instead, the eigenstates are U even and U odd. So U even and U odd actually time evolve at different rate, and the time evolution corresponding to the U even is this e to the minus capital E even t over h bar. You need to actually use this corresponding eigenenergy when you time evolve the Schrödinger states. And likewise, the U odds is actually time evolved with this exponential factor e to the minus I capital E odd t over h bar. So then you know that even though the state initially is in a right well state, but this oscillation are not the same in time, because the first term actually goes like a frequency like capital E over h bar. It's called omega E, and omega R is like capital E odd over h bar. So, and therefore you have evolved the initial state to the different state after t starts to evolve, and at any given finite time, so this state is no longer the initial state anymore, because initial state is a state when t equals 0, which is simply says U even plus U odd, but at the time t, the state is no longer, the same, and you will see that you will evolve the states into the different well. So you could actually see this evolution if you pull out this factor, say the even part of the oscillation, you get U even plus U odd times e to the minus I E even minus E odd eigenenergy times t over h bar. Right? Okay, so you could actually pull this time evolution factor out of this bracket, and then you could rewrite this time evolution in terms of simply the U even plus U odd times an extra phase factor. This is the extra factor. And this is the source of the oscillation. And you can see that when your time goes to T1, which is h bar pi over delta E, and delta E is the difference between E even and E odd. So if your time goes to t1, which is h bar pi time, divided by delta E, delta capital E, then you'll find that the state is exactly on the other side of the well, because this extra phase factor is actually e to the I or minus I pi, which is minus 1. As a result, when t goes to t1 and your eigenstates u of x t1 goes to this state, u even minus u odd, instead of u even plus u odd, and which is precisely u left, right? So you start your state at t equals 0 on the right, but after some time, say t1, and your state is actually u left. Okay? Of course, you could oscillate this particle back to this u right if you just spend twice as much time as t1. Say when t goes to 2 times t1, your particle actually go back to the right state initially, and then when the time equals to 3 times t1, the particle is on the left, and then 4 times t1 on the right, and so on and so forth. So the particle is actually bouncing between these two wells with the same period. And this is called oscillation. And the oscillation between these two wells is precisely due to the quantum mechanical effect. And it's because the time evolution of a Schrödinger state. All right, so, and this phenomena is real because you could see many physical and chemical systems show such a quantum 2 well nature or quantum 2 level structures. Our textbooks just show you a very well-known example, which is ammonia, and that's 3. So this is a lattice of ammonia, which has this kind of a pyramid structure, and this ammonia has this 3 hydrogen atom connected to 1 nitrogen atom, and this nitrogen atom can actually have 2 possible positions, one above the triangle, another is below the triangle. So these 2 positions are the 2 possible stable positions for the nitrogen atom to live. So the nitrogen atom can actually live near one of these 2 positions, top or bottom, and these 2 positions play the similar role as a double well, because these are the 2 stable points that this nitrogen atom could state. So the nitrogen could fall to either of these 2 potential well, but of course the nitrogen can oscillate between these 2 positions, and this is precisely what the physicists, experimentalists see, that this nitrogen oscillates between these 2 positions, these 2 levels or minima potential. Okay, and this oscillation frequency can also be measured in the lab, and this can correspond precisely to this t1 time. All right, okay, good. So, and this kind of a tunneling between this quantum 2 well is also a basis of nanotechnology. For example, this quantum 2 level system in quantum dot or a qubit or quantum bit, which is simply 2 possible quantum states which we could label as state 1 or state 2, or state 0 or state 1, and this forms a basis of a qubit, a quantum bit, and the quantum bit is the foundation, is a basic unit when we build up the quantum computer. And any quantum states could be a linear superposition of state 0 and state 1, which is the analogy of this Schrödinger's cat problem, that a cat can be a linear combination of a alive or dead, right? If you know this story of Schrödinger's cat. But of course, the cat is a macroscopic object that we are talking about atomic level problems. So in the atomic level problem, quantum mechanics dominates. Okay, so you could imagine that this quantum states in this two-level system could be in a linear combinations of 0 and 1. And if you look at this time evolution, and this is exactly what happens, so at any given time, the state is actually a linear combination of u even and u odd, with arbitrary phase at any given time, right? Okay. So, and this linear superposition of two eigenstates in this double well is really, really useful in this quantum technology. But the simplest version of this quantum two-level system is precisely this double well problem right here. So welcome to the quantum world. So now if you continue studying quantum mechanics or quantum technology or quantum information processes, you will see this double well structure over and over a million of times. Okay, so this will not happen in the classical mechanics. In the classical world, no such a thing as a quantum oscillation, but in quantum mechanics, this is allowed. And this is a new feature that is provided by quantum mechanics. Okay, great. So you can see that we don't need to really solve this double well problem by solving the Schrödinger equation of the double well, which is really complicated. We only need the reasoning and argument and approximations. And this is the thing that you need to understand and you need to know. So if you don't have further questions, so we will start a new subsection, which is the potential barrier problem. Let's take a short break. Yeah, of course. This is a good question. So the temperature will actually affect such oscillation on ammonia, for example, as a quantum two-level system. And if you look at this problem and at finite temperature, yeah, of course, there's a higher probability that this ammonia atom, the nitrogen atom, can actually go to the other side. But of course, quantum mechanics also will actually bring this atom back and forth. But if you increase the temperature, so it's the room temperature, and the quantum mechanical effect disappears. And therefore, this quantum oscillation phenomena occurs only in the quantum regime. Okay, so the quantum mechanical regime, as already mentioned many, many times, occurs at very small length scale, atomic length scale, and a very low temperature, like almost absolute zero temperature. So the absolute zero temperature corresponds to 0 Kelvin. So you could actually convert this temperature in Celsius and Kelvin, and in the quantum regime, the temperature is almost 0 degrees in Kelvin, which is minus 237 in Celsius. But if you keep increasing your temperature to almost room temperature, like 300 Kelvin, and all this almost this quantum mechanical effect is actually washed out, because you don't see this oscillation anymore if you are in the room temperature. But of course, the thermal effect will actually compete with the quantum mechanical effect. But as long as your temperature is controlled at maybe in the nitrogen, liquid nitrogen temperature, like minus 100 degrees Celsius, and you can still see this quantum mechanical effect. In many quantum mechanical systems, you could see this quantum effect even at room temperature. So my answer to your question is that temperatures for sure will suppress the quantum mechanical effect, but as long as you keep your temperature to a low enough temperature, then this effect still can be observed. So how low is your low temperature? As I mentioned, maybe minus 100 degrees Celsius or approximately that range, many quantum mechanical effects will emerge. But depending on the material and system, many quantum systems or quantum phenomena can be observed at much higher temperature, almost close to room temperature. So let's look at the related problem, which is the potential barrier. And a potential barrier is the inverse of the potential well. If you simply just flipped your potential well, and this becomes a potential barrier like this. As I mentioned many times, that for this kind of a barrier potential, you have a very interesting phenomena called quantum tunneling, meaning a particle can actually tunnel through the barrier to the other side. So even if this initial energy is actually below your potential strength, V0, even if this is the case, you can still see electron or particle actually tunnel through this barrier, and this is called the quantum tunneling effect. And the quantum tunneling effect is a very important quantum effect and it leads to many technology, such as the STM or many other quantum mechanical instruments, and we will talk about this quantum tunneling phenomena. But you could take advantage of your solutions for a potential well problem, and you simply just invert your potential from V0 to minus V0, or suppose this is your potential well problem, and you simply just flip your potential well. And that will be all. And as a result, we don't need to solve this Schrödinger equations from the beginning. We can simply just take advantage of what we know already from this potential well problem, and then you simply just convert this, make this conversion between minus V0 to plus V0, and then you actually get the solution for this potential barrier problem. So let's just look at these two different cases. One is when you are inside this barrier, or in between this plus minus a of x, and you can easily find this equation that's inside this barrier or in between this plus minus a. So we can define a variable called kappa or kappa squared. So of course kappa is a real number, but you know that this capital E is actually less than V0, so this turns negative, but there's a minus sign here, so that this kappa is real, okay, or kappa squared is a positive. So your solution is this exponential type of solution, which is a combination of exponential increase and decrease function of x when the particle is actually inside this barrier with the proper coefficient a and b. And when this particle is out of this barrier and you have oscillatory solutions, and there are two types of solutions. One is the transmitted wave, which is this part on the right, capital T, which is the transmission coefficient times this free propagating wave, e to the ikx, where k is simply just a free particle wave number. And on the left, you have this incoming particle, e to the ikx, and also the reflected wave, capital R, e to the minus ikx, as usual. So you sum of these two, you get this. So I do not need to repeat this calculation. The only thing I need to say is that this Q in the potential well problem, when you actually make such a conversion between this minus V0 and plus V0, this little Q goes like I times kappa in the barrier problem. So in the potential well problem, remember the particle can be inside the well, but the solution for the particle inside the well is actually the linear combination of a sine cosine function, right? Remember that. But now, since you flip the sign of V0, this inside the barrier potential energy V0 is greater than your incoming energy capital E, so that the solution inside the barrier is no longer a sine cosine function. Instead, it is the exponential function, right? And so this makes a huge difference between this potential well and potential barrier problem, because we will see just a moment later that when the particle is trapped inside the barrier, and you know that the particle needs to be inside the barrier in order to make sense all of this, that the particle can penetrate through the barrier. But the tricky thing is that you have no way to know whether the particle is ever live inside the barrier, because when you calculate this, the flux, there's no flux in the middle. As I mentioned, the flux is the only way that we can detect whether there's a particle somewhere in quantum mechanical problem. If you don't have a way to detect this flux, or the flux is zero, then we don't have any tool or any way to detect whether the particle is ever being inside the barrier. But we know that the particle has to be there. Otherwise, it makes no sense that the particle suddenly disappeared inside the barrier and suddenly reappeared when it tunnels through the barrier. And this is the most tricky part of quantum mechanics, that the quantum tunneling phenomena is real phenomena. It has been observed experimentally for many, many years, but we have no knowledge of detecting such a particle inside the barrier. We have to assume that the wave function should exist inside the barrier, but we have no way of detecting this particle inside the barrier. And we will come back to this point later to emphasize that if we would like to know the particle inside the barrier and we destroy the whole thing, meaning this transmitted wave is gone. There's no quantum tunneling if we really want to know whether the particle is ever inside the barrier. So this contradicts with the Heisenberg uncertainty relation that we emphasized many, many times at the beginning, and the Heisenberg principle, is everywhere. So the Heisenberg principle is here to actually resolve this seemingly inconsistent or very strange phenomenon. So we will come back to this later, but here let me just show you this solution. It's a bit complicated. You could check your textbook. So I recommend that you should derive this formula by yourself once in your lifetime, which is now. But I will not, time is up, but let me just make a final remark. So again, I will not put this kind of calculation in your midterm exam, and therefore there's no reason to remember this complicated factor. Don't remember. You need to derive this, but don't memorize this. Do you know what I'm saying? Do not force yourself to memorize this. This is useless. You need to derive this. That's the point. And therefore, I will not put this as the most important part in the midterm exam, but eventually you need to convince yourself that these are the solutions. And this is very important, but some midterm exam problems will be related to this transmission coefficient or reflection coefficient, but in a simpler way. And I guess that's all for today. And then we will continue this potential barrier on Wednesday.